After class, I'd like to talk to you. You're under the gun now. No, and you. Don't smile so much. So, because might as well tell you, next, on Thursday, the reason I can't come is that I'm going to be busy with your institute, and I'd like some feedback from you about some things about your institute.
What about me?
Huh?
What about him? He's also
Yes, please. Huh?
He's also from IIT, forgot to mention.
Yeah. No, because I couldn't see him, he was kind of hidden behind Parveen. Okay, so last time I was trying to go through the so-called Gelfand, Neumann, Siegel construction. Did I mention that to you before? That whole procedure whereby you start with the state or a C-star algebra and you construct a representation of the C-star algebra is called is the Gelfand, Neumann. Somebody should write it down. Is often just condensed to GLS. So when you say GNS construction, this is what you mean. This is a procedure whereby you start with the state let me just say in A star plus, that means a positive linear functional phi. You start with the phi and then from here you go to you construct a representation. So in fact I'll write it this way. You construct a Hilbert space depending on phi with a certain cyclic vector which I'll denote by phi, psi phi, and a representation pi phi. This whole thing is called the GNS construction. What are all these animals? First, this is a Hilbert space. And second, this is a vector in here. Psi phi is a vector in there. And pi phi is a representation from A to B of H. Representation, and they're all related by the relation is there. So there one pi phi A psi phi closure is H phi. That means that psi phi is a cyclic vector. For the representation pi phi. The cyclic vector means when you move it around by the algebra, you get all of the Hilbert space, and more importantly, you can recover the initial functional phi from the representation of this vector by the equation pi phi x C phi. And so the theorem says that, so the GNS theorem is that there exists such a triple as above. Which is unique up to unitary equivalence. Right? If you don't see what there is, you should be able to guess what that means. And as we'll go through the proof. So we were going through the proof. So last time what we had done was we had constructed the Hilbert's first H phi, and we had also so last time what we'd done was we'd constructed I remind you that what we'd done was that from this phi we defined an inner product on A by actually to get an inner product I should write x hat, y hat equal to phi of y star x. The inner product was actually not quite on A. Initially, a priori, it was a pre or semi inner product on A. It wasn't definite. So you had to mod out by the radical, and then the image in the radical is what you call the thing with the hat. So this is and H phi was defined by A mod in the radical phi completely. There is this one we verified this is a sesquilinear form, and so it is and on this quotient space it defines a genuine inner product. And what we had shown was that we had shown that for each x in A, there exists a unique operator which I call pi phi of x in B of H phi, such that pi phi x would send a y hat to xy the whole hat. And then what is that cyclic vector? Psi phi is just one hat. Because the image of when you move one around by A, you will get all x hats, and that is by definition dense in the Hilbert space. So this is a cyclic vector, and we do have a representation. So we have one problem. We have to verify that the pi phi is a representation. So let's come to this later. So from the equation, isn't it clear that except for the fact that you put hats, it is just like drift multiplication by things in A. It must be clear that this pi phi is a linear map and that it is multiplicative. Pi phi of xy is pi phi x, pi phi y. Probably the only thing which is not totally obvious, and we've shown also that In fact, pi phi is contracted. We've shown that norm pi phi x is less than or equal to norm x. That is how we obtained this. We got this mapping on the entire Hilbert space. We first verified that it was a bounded operator on this pre-Hilbert space with bound given by norm x, and so it extends to closure. Okay, so probably the only thing that is not completely obvious is that it preserves the adjoints. So what should I check? So I should check that pi phi x y hat of anything of any zeta equal to y hat. No, I should prove that pi phi x eta, this equals eta in a product pi phi of x star zeta for all eta zeta in H. That is what it means to say that pi phi of x star is the adjoint of pi phi of x. Right? And rather than verifying this identity for all vectors in the Hilbert space, because all the operators in question are continuous, it is enough to check them on a dense subspace. So it is enough to prove that I may take eta to be some y hat and zeta to be a z hat with yz in A. Because things like that by definition are dense. Right? Now if eta was y hat and zeta was z hat, what is the left hand side? Then the left hand side becomes equal to phi of z star times xy. Because pi phi x of y hat will be the hat of xy. The inner product of xy hat with z hat is by definition phi of z star by xy. And this you do a little sleight of hand and you observe that this is the same as star z, the whole star y. I just rewrite that z star x as the adjoint of x star z. But then what is that? That is then by definition equal to this thing. Right? The right hand, the second vector is going to be xz hat. So y hat inner product xz hat, sorry x star z hat, which is going to be phi of the adjoint of x star z times y. So indeed, one sees that these things, that this is true, and so pi phi start preserving. So we've proved everything that is stated in the last page here, except this uniqueness. And that uniqueness is a typical consequence of what I call the KRP lemma. And if you have two dense spaces We have two total spaces in Hilbert space, indexed with the same thing. If you have an inner product preserving bijection between two total sets in Hilbert space, it will extend to a unitary operator. So that's exactly what you will have if somebody else wants to be such a triple. Indeed, if pi h, pi c h is any such triple, then I want to say that there exists a unitary. Okay, see, by definition, in H phi, psi phi is a cyclic vector. So I want to say there exists a unique unitary operator U from H phi to H such that I want to give you two, in this case actually dense subspaces of these two Hilbert spaces, which are both indexed by the same thing. What is the same thing? The same thing is going to be A. They're going to be indexed by A, so I want to say U is going to send pi phi x psi phi equal to pi x psi for all x in A. By assumption, this correction of such thing is dense in H phi, correction of such thing is a dense subspace of H, and I just have to check that this association preserves inner products. Okay. So you just see what the inner product is. For example, what is pi x c inner product pi y x c? Now pi is an adjoint preserving mapping, so I can pull that y over to the left side as a y star, and then I'll have pi of y star pi of x, which is pi of y star x, because pi is an homomorphism, and so this is pi. Well, this is what pi of y star x psi xi. So by the defining requirement that we had relating pi and phi, this is nothing but phi of y star x. Which by definition is exactly what you get if you put pi phi here and psi phi here. Right? So that means you do have an inner product preserving bijection, mapping and bijection. It is a bijection because it's a clear, and since it's inner product preserving, it is a linear mapping, so it's an isometry on this dense subspace. So it extends uniquely to a unitary between the two Hilbert spaces. And it's trivial to see that U is going to send, what is U of psi going to be? Psi phi. Why? Put x equal to 1. Okay. And next I want to say that U pi phi x u star equal to pi x for all x. That is, I want to check that u pi phi x is pi x u. So you check both of them on a dense subspace here, which is all things of the form pi phi y psi phi. So you check both sides on pi phi y xi phi. Both sides will be equal to, what will you go? If you apply u to this thing, you will get just pi y xi, and then you get pi xy psi. So I will refer to this as the GNS triple for phi. For any phi, there is a unique up to unitary equivalence, GNS triple, and you can go back and forth between phi and this. From phi, you can get such a thing, and given any such thing, you can get your phi back. Okay, so this is how one associates a representation to any C-star algebra. We use the fact that it was a C-star algebra in see, this is a useful point to bear in mind, because in other in other areas, one will find the same sort of thing. See, you can do this for A can be just a star algebra. Suppose I just have a star algebra, and suppose I have a phi which is a linear functional, and which is positive. I'm not assuming. So I'm not assuming boundedness of phi or anything. Given any such phi, one can always associate a sesquilinear form by defining d phi of xy equal to phi of y star x. This will be a sesquilinear form defined on this A. So you can do everything that we did before. Right? I can take the closure of that, the completion of that, and I will get a help. No. First I must take the radical of phi, mod out A by the radical of phi, and everything is formed into Cauchy-Schwarz. You don't require anything, you only need positivity, which you have now. So you will have indeed, you can try to do the same thing and associate. You can define H phi by the same way. The same definition makes sense. And you can hope to define a representation pi phi of A on H phi. Now, this is the first time you run into one analytic problem. How do you ensure that there is a representation of A on H phi First, you see that exactly as before, you will see that on the quotient space A mod n phi, because you only use the fact that the radical of a positive form is a left ideal because of the Cauchy-Schwarz inequality. So A will act on the left of the quotient by the left ideal. So for every x, I can define left multiplication by x as not mapping from A mod n phi into itself. But then we need to be able to extend that to the entire Hilbert space. You need to know that map, up till now everything has been purely algebraic. But now you need to know that this operator is bounded. And for that we use various facts about C-star algebras. That if phi is positive, it is automatically bounded and it attains the norm at 1. And conversely, if it attains the norm at 1, it is positive. So we use all this, and it is in extending the representation all the way to the level of the Hilbert space that we require the thing to be a C-star algebra. Sometimes it turns out that even when A is not a C-star algebra, it may be the case that this will extend to representation on this Hilbert space. When that happens, good things come out of that. So this is anyway. So this is what, for example, happened in one case, which is okay. Neumann. Okay, so you will bear in mind that in all this you must keep track of where you are using the hypothesis, which is an analytic property, which is a purely algebraic thing. Up till now everything is algebraic, but going to the completion, that is an analytic thing. And so okay, so much for C-star algebra. So now let me go to von Neumann algebras. So what did all this say? So last time itself I had gone through this thing of how for each element of A or a positive element of A, I can find a phi in A star, a positive element of A star, for which phi of x is norm x and norm phi is 1. And then we're taking direct sums and so on. We showed that by using this GNS construction for enough states on the algebra, you can get a faithful representation of A on Hilbert space. If A was separable, by applying that lemma that I just mentioned for a countable dense set in the C-star algebra, you can ensure that you will get a representation, namely the direct sum of all the GNS representations, which will be a faithful representation on separable Hilbert space. Okay, so now I want to go to the von Neumann context. We want to say all the same things for von Neumann algebras. So here I'm going to kind of cheat a little bit. If we have time, the later the course will do what is needed to justify all the noises I'm making. But the point is that we want, if M is a von Neumann algebra, So this is the abstract definition. So what we want is that there is a faithful, see, in the category of one-hour algebras, what are the morphisms? The sigma weakly continuous star algebra. So we want a sigma weakly continuous star algebra isomorphism of M onto a one-dimensional concrete one-dimensional subalgebra of some B of H. Okay. Yeah. So for the the problem. So where I'm going to wave hands is I'm going to say we'll do exactly the same thing as we did in the C star case, except we won't look at just all positive functionals on A. We look at positive functionals on A which are sigma weakly continuous. Okay, so the definition. Phi in M star right? By M lower star, I mean something in the pre-dual. Then you can think of that as a linear functional acting on M. That M lower star embeds into M upper star by the canonical inclusion of X into X double star. So M lower star acts as functionals on M. So I can talk about functionals on M which are positive. That is, they send positive elements to positive numbers. So such phis are called, in fact, it's used more generally, not just M lower. Let me put it this way: if let me use some other letter. Suppose you have a map between one-dimensional algebras. Is linear, positive, and sigma weakly continuous. We say he is normal. The word normal, the adjective refers to a linear, positive, most importantly sigma weakly continuous map between one-dimensional algebra. Typically we'll use it for in two situations when this E is actually a star algebra homomorphism. Then we'll talk about normal homomorphisms or normal representations. That is when M goes into B of H. Or we'll talk about normal linear functionals. Right? So we'll be interested in that trivial case when N is just scalars or when E is actually a representation. Later, when you get into one-dimensional algebra, there is the other thing that other map that one looks at called conditional expectations and so on, where also this notion is important. Okay, so such a map is normal.
N equals to R or V.
Huh?
Is called normally N is R or V.
No. We say if E is linear, positive, and sigma weakly continuous, we say it is normal. I'm saying we will typically use not R, C. We will typically use it in the situation when N is, there is, either E is already a star algebra homomorphism between one-dimensional algebras, or maybe it is just a linear map and when N is C. In this course, we'll probably you see it only when maybe okay. So we're interested in the normality. Okay, so understanding normality in general is, see, if E maps suppose this sigma weakly continuous, there is in domain and range. So what does that mean? I claim that means that, see, given any map between Banach spaces, you can talk about its adjoint or transpose. You can look at E star, which is a map from N star to M star. Right, which is given by E star of anything if that thing composed with E. That is how you define adjoints at the level of Banach space. If I want to get a map from functionals on N to functionals on M, so suppose you are given a functional on N, then you give me something in M and push it forward by E and then apply the functional on N that you gave me. That result I will call the functional on M, which is E star. So to say it is sigma weakly continuous means that, and this will map because what does sigma weak continuity mean? It means for every, whenever you have something converging here, sigma weakly, that means against things in N star. If I have a net in M, xi converging to X weak star, what does that mean? That means that if I pair xi with any row, for all row in M lower star, right? That is what sigma weak convergence means. But in particular, if I choose this row to be the image of E star, right? If and only if. See, sigma v continuity means you want EXI to convert to EX. V star. That is what continuity will mean. Sigma V continuity means whenever I have weak star convergence in M, the image must weak star converge in N. But this means what? Phi EXI converges to phi EX for all phi in N star. What does that mean? If this happens, that will mean that if you take, I can put E star phi that means what? So what are we saying? Xi converges to X weak star implies that what is that? E star or yes, so it is contained in this, so I'm not saying this right. See, if you know what does it mean to say that E star maps N lower star to M lower star? That means for any phi in N lower star, E star phi must be in M lower star. What does that mean? That means whenever Xi converges to X weak star, E star phi of Xi must converge to E star phi of X. So, right, that is exactly the statement that E star of phi belongs to M lower star. Whenever you have such convergence, you have this convergence. So, all this is just so to check normality, what we have to just see is that if you compose with normal linear functionals, you must get normal linear functionals. If you have a mapping E from M to N, if whenever I compose this E with a normal linear functional on N, I must get a normal linear function on M. Right? So this whole thing, understanding general normal maps, goes down really to understanding normal functionals. And which is where, so I hope we'll be able to prove at least see some indication of the proof. See, there is an old theorem due to, so which we won't prove, so it's a fact. Phi in M star is normal. Okay, in fact, the following are equivalent. So these are conditions for checking normality. See, it is something like, see, a one Neumann algebra is determined by its projections, I have been saying. It is a norm close, it's the Banach space generated by its projections. If you restrict the phi to the projections, in general, if you restrict the linear functionals to a projection, if you go back to the commutative case, suppose M is commutative. Actually, I haven't proved this for you, have I? That if you take a commutative Banach algebra which acts on separable Hilbert space, then it is an L infinity. So think of the example of M being L infinity. So you take some functional on L infinity. It may be integral against some function or something. Any functional on L infinity. It may be L infinity means it is essentially bounded functions. So when I restrict this to its projections, that means I am looking at a function from indicator functions or equivalently from sets. To sets I have positive numbers. This phi will, if I just assume that it is phi in M upper star, see in the commutative case, when M is L infinity, and if you look at phi of an indicator of V, if I call this some nu of V, then to say that phi is an M upper star will mean that phi is linear. Right? It is continuous and linear. So what does it mean to say that nu is linear? Then if E and F are disjoint, then 1 of E union F is 1E plus 1F. That means nu is additive is finitely additive. To say phi is an M upper star will say that nu is finitely additive. But normality is something more. It is like saying you want countable additivity. You want this to be, so you must think of normality as something like countable additivity. Okay? The difference between countable additivity and finite additivity, see, this is M upper star is finite additivity. What is the difference between finite additivity and countable additivity for a measure, for a set function? In measure theory, I know I've given at least the two of you guys this we've proved this fact. Phi is continuous from below. What does that mean? If xi increases to x, that means if xi is a monotone increasing net in M, whose soup is x, that implies that phi xi converges in also. The moment you know phi is countably additive, it means if the fact that xi is increasing will mean that phi xi must increase. But the requirement that it must increase, the supremum must be phi of x, is countable additivity. Right? They like the monotone convergence theorem, for it to hold, you need countable additivity of the measure. So this is one version. Another version is if E I when separable case, so I only need to look at countable are pairwise orthogonal projections in M, then countable additivity. Just countable additivity on the projections is equivalent to Ramanujan. Okay, now this theorem would be, I certainly can't give you a proof off the top of my head. I'd have to prepare to see if I can indeed give you a proof that I can get across to you. Okay. So now let me observe the following thing. So now suppose
normal linear functional on area infinity is measure.
so you tell me what is it? What is M lower star? Normal means it is in M lower star. What is M lower star? If M is L infinity, L1. So it must be a measure which is absolutely continuous with respect to mu. Only then it will make sense as a functional on L infinity. A function which is 0 mu almost everywhere must be sent to 0. Only measures which are absolutely continuous with respect to mu will give you functionals on L infinity mu. Okay. Okay. So usually, even in the C star case, the good case is to prove that there exists a faithful representation of the C star algebra. I went through various calisthenics to construct the direct sum and so on. But in good cases like 0, 1, there will be a canonical candidate for their state. In fact, the big measure, the associated state on C01 is going to be faithful. So here's the definition. What does it mean? How can what does faithful mean for you? 1, 1 is what I've been saying. But how can a linear functional be 1, 1? Unless the space is already one-dimensional, there is no way a linear functional can be 1 to 1. Because it is going into a one-dimensional space. So, in general, we say that a phi in A star, I don't need one dimensional position, just C star. The C star definition will also, a one dimensional algebra is also a C star algebra. Okay. Suppose you have a positive linear function on a C star algebra, is called faithful. What do you think it can mean?
Positive element greater than 5, positive element greater than
positive element.
Positive means already means that.
positive gives positive.
If that is 0, then positive element has to be 0.
Or equivalently what we call the radical must be trivial. If phi of x star x is 0, then x must be 0. Now it should be clear that if you have a faithful, so note phi faithful implies pi phi faithful. So what does that mean? Suppose pi phi of x is 0. Then I want to say that x is 0. If pi phi of x as an operator is 0, then if I act it on 1 hat, pi phi of x equals 0 means x1, that means x hat must be 0. But if x hat is 0, that means the norm of x must be the radical. So x must be 0. Right? So if phi is faithful, then pi phi is necessarily faithful, but the converse is not true. Okay. See, pi phi faithful means pi phi is 1 to 1. That means its kernel is 0. So, see, this says there's some slight subtle point. See, this statement is equivalent to saying that kernel pi phi is 0. This is an ideal. Kernel of pi phi, because pi phi is a representation, its kernel is an ideal in name. Whereas this is about saying that the radical is 0, which is a left ideal. So there is a difference between the two. You can come up with examples where see, if your algebra had no ideals, Like for example the matrix algebra, it has no two-sided idea. Then every representation, if it is unital, since one-to-one, has to be faithful. Because the only ideals are zero or everything. Right? But there are certainly positive functionals on the matrix algebra. And take the 1-1 entry of the matrix. That is a positive functional. But that is not faithful. But if you do the GNS for that, this is probably a good it's a digression worth going into. Look at why I mean, look at A equal to B of H itself. And take psi to be any unit vector. Define phi of x to be x psi psi. X is by a priori already an operator. So here is a positive, here is the state of the C star algebra. Can you tell me what is GNS triple is? The GNS triple is unique. So there will be a Hilbert space, a representation and a cyclic vector which returns this functional. And notice that GNS triple is unique, so you don't have to go through the construction to find out what the thing is. If you have any triple which works, then that is the thing. So what is a natural Hilbert space, a representation of this thing, and a vector in that Hilbert space? So it's going to be H psi 8H. Height B of H. Just the identity representation. B of H as operators on H. So this is the GNS triple for this thing. So if you take, now let me, I'll keep digressing. So let me go back to, I started talking about the von Neumann context. So the good case is when if M, so let me say this is proper. The von Neumann algebra with a faithful normal state. state in a C-star algebra always means a positive functional, so that phi of 1 is 1. Suppose you have one, actually the state is only a normalization, it is not important because the moment phi is positive, by the Schwarz inequality, if phi of 1 is 0, then phi of everything is 0. So if phi is non-zero, you can normalize and assume that phi of 1 is 1. So the state is just a non-trivial normalization that you're doing. So if the one-dimensional algebra admits a faithful normal state, one says then pi phi is a normal binormal normal. That means it is normal and the inverse is also normal. Or it's a normal representation onto a one-dimensional algebra. There is, at least for such one-dimensional algebras, I would have proved the that abstract versus concrete thing. If an abstract one-dimensional algebra, so here I mean, I'm thinking of in the abstract setting. I'm not assuming it as straight down to Hilbert space. I have some one-dimensional algebra which admits a faithful normal state. Then it admits, then the GNS representation is an isomorphism of M in the category of one-dimensional algebras onto this one-dimensional subalgebra of B of H phi, onto this concrete one-dimensional algebra. One is saying that the image is one-dimensional algebra and this thing. So the only thing that one has to see, since phi is faithful, pi phi is also faithful. Right? Purely at the C-star level we have seen this. And why is it normal? Because to see it is normal, I was say that if it's enough to check that. So here's the exercise. So lemma. If I have E mapping M to N, linear, but these are one-dimensional algebras. I want to say E is normal that is exactly the criterion I gave for functionals I want to give. For functionals I said if it must respect monotone convergence. There is xi increases to x implies exi increases to ex. Why this criterion is satisfied by functionals? And to say that E is normal, see, what should I check? I have to check that if phi in, okay, so let's see this. See, see, to see normal, I made these noises earlier. To say that E is normal, the same as saying that E maps, E star maps in lower star into M lower star. That means if I take a phi in E, continuing from here, phi in N star implies phi composed with E is an M star. So this is what I have to check. But I know how to check for linear functionals whether they are normal. So that they will, for this will happen if and only if whenever xi converges to x, phi of exi increases to phi of ex whenever xi converges to x, increases to x. Right? Should I have to write anything more in everything? I want to check that phi in N star, that is, I want to check that phi circle E preserves monotone convergence. That's what I have to check. That means whenever I have xi converging, increasing to x, phi of exi converges to phi of ex for all phi in N star. That is the same as saying that exi converges to ex weakly. Weak star, which is the same as saying exi increases to x. Okay, so why I said this was I want to check that pi phi is normal. So I need to check that if xi increases to x, whether pi phi xi increases to pi phi x. To say that a family, it is clear that, that this family is increasing. So I have to check that the limit is this. That is what I have to verify. That is, we know that pi phi xi converges in any topology that you want, strong operator, weak operator, whatever. So all this is assuming that xi is a bounded net, bounded increasing net. 2 pi phi of x. Now, I've used this lemma repeatedly before to say that a family of now there is a bounded family of operators which are uniformly bounded. They are bounded by the norm of, see, if xi increases, norm xi is going to be less than or equal to norm x for every x. So norm pi phi xi will be less than or equal to norm pi phi x for all x. So all the pi phi xi are uniformly bounded. If you have a uniformly bounded family of operators, to verify strong SOD convergence, it is enough to check it on a total set. That is on a dense set. And here the natural dense set to check it on things like, see, on things like y hat. Things like y hat, y and m are by definition a dense family in H phi. And if you acted on y, then, or let us check that weak operator topology. Look at pi phi xi, y hat, y hat. What is this? Phi of y star xi y. Now phi is positive and x squared to y star xy is also positive. And then there is a continuous map. So this will clearly increase to phi of y star xy. You don't quite need, you don't need increasing, just that you just have to know that the limit of this is equal to this, which one has because phi is normal. Because phi is normal, it preserves this increasing limit, and so you have this limiting state. That means that pi phi is normal. Pi phi is normal and it is faithful. Faithful means already at the level of C-star algebras, it means that it is an isometry. Right? We've seen this before, right? Any faithful map of C-star algebras is an isometry. That means pi phi must map the unit ball of M into the unit ball of M. That is, if pi phi maps the unit ball of M onto the unit ball of pi phi M. But the unit ball of M is, what can you say about that? M is a one-Neumann algebra. It is sigma weakly compact. And pi phi is sigma weakly continuous. So that means the unit ball of pi phi M must be sigma weakly compact. And we had seen in one of the earlier classes that for a star algebra, the unit ball being sigma weakly closed is equivalent to the thing we have one-Neumann algebra. That means that shows that pi phi of M is a one-Neumann algebra. And so this is proved, completed the circle. That is assuming that you know that you can find a faithful normal state on a on a separable in a one-Neumann algebra acting on a separable Hilbert space. I am claiming you can always find a faithful normal state. Why? I just, as I stopped the last suppose En is an orthonormal basis, psi n. Let me define phi of x equal to summation 1 by 2 to the n x psi n psi n. First, phi is positive and it is in the closure of the I want to say this is normal. So, but we know what the thing, we know what trace class operators do. This is exactly trace of x rho where rho is something like this is the trace class operator because this 1 over 2 to the n is summable. So this is a normal state on all of B of H, a sigma weakly continuous. So if you restrict it to the image of so here I am assuming that M is contained in B of H. See, one is observing that phi is actually a faithful normal state on B of H. It is normal, it is a state, and it is faithful. Why is it faithful? Because the phi x is 0. If phi of x star x is 0, then what does it say? We put x star x, that will say that x I n must be 0 for all n. And so if x gives an entire orthonormal basis, then it had better be 0. So it is indeed faithful. So any one-Neumann algebra acting on a separable Hilbert space admits a faithful normal state. And okay, this is kind of cheating, but those are the only ones you can hope to get in this fashion. If you want to be able to represent M faithfully on separable Hilbert space, it's the kind of circular reasoning, but anyway, so let's. So we won't meet next Thursday. We only meet on Tuesday.